Let's start our final session today. Only one talk, so the presenter is
Haltin.
who?
Haltin.
Haltin.
Yes. Haltin.
Haltin. Okay, the talk is on the slide.
Yes.
So please.
Okay. Thanks. Let me turn this on. Hello. Okay. So thanks for the invitation. My name is Haltin. And this is a joint work with Stefano, who is a researcher in Lawrence Berkeley Lab, and You Chao, who is in Princeton. The title is Alternating Projection and Ptychography and High-Dimensional Phase Retrieval. So the first slide is the motivation of the work. Actually, if you take a look on the left-hand side, this is the cover of the latest spatial issue in the journal Nature. The subtitle is Crystallography Turns 100 Years Old. So let's quickly review what we have been achieved by this technology. In 1914, the sodium chloride atomic structure was determined by this technology. In 1952, it's well known that we found the structure of DNA as Watson-Crick. And after 50 years, finally, the complicated structure RNA has been determined in 2001. So there's quite a lot left that I don't mention. We asked our own a question. It has been 100 years. What can we do in the next 100 years? Is it possible? We have a dream saying that, is it possible that we get an atomic resolution image of a very huge object? For example, this is the Earth. Is it possible we get the whole image of the Earth with atomic resolution? It's a dream, but we ask, how to carry this out? So we want to measure macro-scale samples at atomic resolution. Okay, is it possible? The answer is yes. The main ideas are the following two things. First is diffraction. Diffractive images allow us to get atomic resolution. The second idea is scanning microscopy, which enable us to image macro-scale objects. If we combine these two thinking processes together, the technology is called ptychographic imaging. So how does it work out? We have a sample in the middle, which is a large one. We have X-ray on the left-hand side, which is the X-ray generated by the synchrotron. It's a monochronic X-ray. Then we have a small focus on the sample. We get a diffractive image, diffractive pattern of this small area. And then we move this lens across the sample. We get several different diffractive images. So in the very end, we get a pile of diffractive images. Each of them are associated with a different area inside the huge sample. Now we ask our own question, is it possible to recover the sample from this diffractive image? Before we go to the detail, I will show you some numbers so that you have a feeling about this experiment. This is the current experiment, the sample size. This sample size is about 4 micrometer by 4 micrometer. The lens size is about 70 nanometer by 70 nanometer. And when we move the lens, the overlap is about half lens radius. The sampling rate of the diffractive pattern is about 1,000 by 1,000. So in the very end, for this small sample, you will get 10 to the 10 pixels. And in the near future, by near future, we mean the Q4 season this year, we will get a much faster CCD so that the data acquisition, the data will become much larger, 1,000 times larger. And we are going to scan like a millimeter scale samples. So you can imagine that, yes?
Of the X-ray beam.
Okay, excuse me?
The coherence length.
Yes.
coherent, but what is its coherent size?
You mean which one? This size?
No, the coherence length. So you say it's a coherent beam, comes from a synchrotron?
Oh, okay. You mean the length of the X-ray, the wavelength of the X-ray?
No, the coherence length. It's essentially the scale over which the thing loses coherence, right? So the beam is not purely monochromatic. It has some finite width and frequency, which defines a coherence time, and from this there is a coherence length.
Oh, okay. Sorry, I cannot answer this question. Oh, I don't know the experimental parameter here.
It determines the resolution you can achieve.
Yes, but I don't know the precise number here. I can, if you have interest, I can answer you later.
Okay,
I can ask
thank you.
Okay. Okay, so it's the big data. So how does it look like mathematically? So we have this sample, which is of size n by n, and we can pile on all the pixels in n square vectors. So this psi is our sample, and we have this this vector to present the sample. Now we have a length. This is the character. This is the function which characterizes the length, and this length is of size m by m. And we move the length across the window, across the sample, and for every point, for the length, we move to x1 and x2 and x3 and so on. And for every position, we take a diffractive image. So it looks in the following way. We have a big matrix Q, which is of size k m squared by n squared, where k is the number of the illumination windows, the number of diffractive images we want to get. And this matrix, big matrix, means that we will chop the small, we will crop a small area of the sample and multiply by the window, the window function, this length function. And in the very end, we get several illumination windows denoted by Zi. And I is from 1 to k. Then, for every illumination window, we take the Fourier transform. Then we take absolute value. That will be our model of the diffractive images. So we get in the very end k diffractive images denoted as AI, and we can pile them on as a big matrix, which is data. It's RKM squared length. Now the question is, how can we recover psi from A? So the formula looks now like A is absolute value of FQ psi. Note that the phase of FQ psi is missing. We don't have the phase information because we take the absolute value pixel by pixel. And we want to recover, if we want to recover psi, the first thing we have to do is to recover the phase. And this is called a phase retrieval problem. So before I discuss the mathematical details, let's take a look in the current results, like this from that David Shapiro, who is also a researcher in Lawrence Berkeley, used this technique to image this green cement. On the left-hand side, this is the traditional scanning microscope. The resolution is about 300 nanometer. On the right-hand side is the result of ptychography. The resolution is about 15 nanometer. And the size of the sample is about 4 micron by 4 micron, as you can see, as I told you before. So you can see that with ptychography, we can obtain a much finer structure of the object we have interest. And this is the prototype called Nanosphere in Lawrence Berkeley, which looks like this guy sample here in the CCD. And the experiment has been carried out in this machine. So in this talk, there will be 3 main topics. The first one is phase retrieval. The second one is alternating projection algorithm, which is the algorithm commonly used in the field to reconstruct psi from A. And we will show that there is a global convergence property of this algorithm. And later, I will show you like a ptychographic image problem and phase synchronization, how to efficiently obtain the phase simply from the amplitude. Okay, so first part, phase retrieval problem. The mathematical framework of phase retrieval. This will be a more general framework as before, compared with before. Now, imagine that the image space is Cn. If I give you an object psi 0, and I give you a frame inside Cn, which is an over-complete kind of basis. M with M, a frame is actually a set of vectors inside Cn. And we know that if M is less than n, then there is no way we can span the whole space. And if M is greater than or equal to n, then we have a chance. And in particular, if M is equal to n, we know this basis and so on. And we put all the frames, all the vectors in the frame, Fi, and take conjugate as a rows, and form a matrix, M by n matrix called S. This is a setup. The phase retrieval problem is the following. I give you A, which is absolute value of S psi 0. By absolute value, we mean we take absolute value entry by entry, just like you view the vector as a function. The question is it possible to recover psi 0 from A? Note that the phase information is missing. Before continuing, there is a spatial structure inside this problem I have to mention. The S psi 0 is actually located in a torus. It's a torus embedded inside Cm. And this torus is a bit spatial. Not very spatial, looks very friendly, but it turns out to be kind of evil from my viewpoint, quite difficult to deal with. TA is a real torus inside a complex space, so you have to play in between complex and the real structure. The TA is actually a set of vectors so that its ice, the modulation of its ice entry is just AI. And this is the illumination picture looks like this. For every detector pixel, you will have a circle. The circle, the radius of the circle describes the amplitude modulation of S psi 0, and the phase, the angle describes the phase. And notice that A is also in TA. So later on, when I say torus, it means this TA. There are several questions we have to ask ourselves before continuing. This, in particular, for this phase retrieval problem, it's a kind of inverse problem. First one is uniqueness. Is it possible that you find two different objects so that its modulation of coefficients are the same, with related to the frame? And this kind of problem has been studied for a long time. Most of them focus on real images. In particular, images have positive amplitude, and the frames are oversampled Fourier transform, and the dimension of the image has to be greater than 1, and so on. And they only focus on genetic images. There's one particular uniqueness result which we count on is the result by Balan, Casaza, and Edidin in 2006, which we will discuss later. With this uniqueness result, we may say, okay, fine, this map is this kind of mapping is unique, but how to reconstruct psi? You will see later that this is a highly nonlinear thing, so it's not that easy. And several algorithms have been proposed in the field to solve this question. For example, alternating projection algorithm, AP algorithm, error reduction, which was proposed in 1972. It has been quite widely used in the field. And this HIO algorithm, raw algorithm, and several others. That sounds good. However, there's a main issue. Up to now, there is no theoretical guarantee of the convergence of all these algorithms. People just try, and different teams use different algorithms, and they compare to each other. Somehow it's a bit like black box. So the whole one of the main topic in this talk is we will show you that for the AP algorithm, actually we have global convergence. This can be obtained. And to show the global convergence, we need the uniqueness result. So this is the uniqueness result I will discuss. So if you remember before, I showed you that for a friend, I will write a matrix S. This is S, which is a friend. It tells you this map means that you evaluate the coefficient of a vector in Cn associated with the friend. So it's Sz is the coefficient of Z which is related to the friend. And then you can imagine that S is actually, if you view the columns will form actually a basis of a subspace, n-dimensional subspace embedded in Cm. M is greater than n, so that for all image space, after this S map, it will become a low-dimensional subspace inside Cm. And all these subspace can be quantified by Grassmannian manifold of Mn. The phase retrieval problem is actually formulated as the following nonlinear map, which I denoted as MSA. What you have is Cn, you map Cn to R, M plus. R plus means the positive real value. What you do is you just evaluate Sz and you take absolute value entry-wisely. Why do we have this T? Why do we mark out this T1? The T1 is actually a global phase. What does it mean? For given Z, if you multiply by just by a T1 effect, which is exponential to IT, which is like a unitary complex value, then you can see that you can view this as just a constant. So all the linear evaluation S doesn't effect is not influenced. In particular, after taking absolute value, this global phase just disappears. So the global phase will be marked out because we don't care about it, and it will introduce some confusion when we discuss the uniqueness. The theory by Balan and Casala says that if M is large enough, in particular M is greater and equal to 4n minus 2, then MSA is 1, 1 for a generic frame. What does it mean? By generic, I mean that on the Grassmannian manifold, it is an open dense subset. So for almost, if you put a probability measure on the Grassmannian manifold, and it tells you that with probability 1, all the friends you choose will have this 1, 1 property. This is kind of the picture of this relationship. This is Grassmannian. It's a base manifold, and you can view the frame bundle, all the frame as a manifold, which has a base manifold as Grassmannian. And the fiber is GLNC. And the bed manifold is bed friends, which means that the MSA is not 1, 1. It's just a small subset. So this is the uniqueness result we will count on. It tells you that suppose the friend is redundant enough, then you are good. Don't worry. But still, it doesn't tell us any more information. Still, we don't know how to reconstruct psi from the amplitude information. The diffractive image is still there. We don't know how to do it. We need a way to evaluate it. Notice that there are two pieces of information in the data. If we trace the problem, the first part is that the solution always lives in the range of S, which I denoted as RS. It has a correct phase. Second part is the solution has the amplitude A. Sure, because we take absolute value, we get A, so we must have amplitude A. It's correct amplitude. So somehow we want to play to take these two pieces of information into account. How to do it? We define these two operators in the ambient space Cm. The PS is the projection operator, which will project everything onto the range of S. It's a projection. The second one is just the amplitude modification operator. Which you do is you map every vertex, every vector. You project every vector to TA. And how do you do it? You keep all the phase information, but you replace the amplitude information by A. And you can prove that this is really a projection. And that everything is entry-wise. You do deviation, you take absolute value entry-wisely, you do deviation entry-wisely, and you multiply by A entry-wisely. Just like you view all the vectors as functions. So now we have two operators. One is projecting to the range of S. Another one is you project to TA. Now, in 1972, the alternating projection algorithm was introduced. How does it work? The yellow plane is the range of PS, RS, and that curve is the torus TA. It doesn't look like a torus, I know. The main reason I draw it in this way is I want to reflect, to emphasize its nonlinear mapping nature. And we have S psi, which is a ground truth. We know it. But as I told you, the global phase doesn't change anything. So in the very end, the real solution set we have interest will be denoted by SA, which is EIT S psi. Now the algorithm start. We start from a random phase. That is, and we just put it to A, and here the random phase means the phase are all 0. For every entry, the phase are at 0, and we put everything to A. So this is PA zeta 0 is just A, and now we know that the amplitude information is correct. The phase is kind of wrong. So what do? We project back to RS. We hope that after projection we get the right phase. But unfortunately, after projection, the amplitude, the phase may be correct, but the amplitude is wrong. So what do? We project it back to TA. We get the right amplitude, but again, the phase will be wrong because it will no longer or may not be live in RS. Then what we do is we keep doing this. We project back to RS, and we hope that at some time we get a convergence. And after this algorithm was proposed, people used it and they found it quite successful, but it may be slow. So there are several variant algorithms following this algorithm, and so on. As I mentioned, the main issue in all these algorithms is the following: convergence. Can you guarantee anything about convergence? Maybe you just converge to nothing. But you just view that nothing as something. You need something to guarantee. So in 1990 or 2002, there are some local convergence result of the algorithm proposed, but they need some non-trivial conditions which are not that easy to check in practice. For convergence rate by Luke in 2008, there are some local linear convergence results, but again, they need some non-trivial conditions, which is not easy to be checked. So we want to answer this question: global convergence. The theory we have right now is when m is greater and equal to 4 or minus 2, and RS is generic, then AP algorithm always converge. But it may be very, very slow. So slow that you may never see the convergence in your lifetime. How to do the proof? I will very quickly show you the proof. The main idea behind the proof is understanding the stagnation set. Now, remember that right now we have an alternating projection algorithm. We project in between two sets. And it is possible that at some time, this projection, this kind of iterative algorithm just stagnate. What does it mean? It means that no matter how you do, PA, PS, PA, PS, you just keep steady state at one point. Is it possible? Yes, it is possible. If it is possible, then it means that we have to be very careful about the AP algorithm, because maybe at some point we just get trapped in some bad set. We want to control it. And notice that the solution is in this set. Because remember, if zeta is really the solution, then zeta, PA zeta, will become zeta again, because the amplitude is true. PS, PA zeta will become zeta again, because phase is true. So everything is true. So you get PS, PA zeta is zeta. So the solution is in this stagnation set. So somehow, when we enter a stagnation set, we may say, oh, well, maybe we are the solution. But let's see. This is the main theory of the proof, which tells you that this stagnation set is actually the intersection of RS and the TA. RS is the range of S. TA is the torus we have interest. And you know that TA is a complicated real torus inside CM complex space, so this intersection may be very complicated. But it turns out that it's not so crazy. In particular, when M is greater than or equal to 4 or minus 2, and RS is generic, then the intersection is just the solution set. So it tells us that if we have a generic friend, and the M is larger enough, in particular M is greater than 4 and minus 2, then the only place we will get into stagnation is the solution set. With this theory, we can show people that this PA minus A or PS minus A operator, they are kind of contractive. What it says is PA minus AI acting on zeta L, which is the Lth step of the alternating projection algorithm, will be always less than the previous step. And there will be some alpha L, which is less than 1 value. But notice that the alpha L sounds reasonable to say something, but if you think more carefully, suppose alpha L is always less than something 1 minus epsilon, then you get linear convergence globally. But however, the only thing I can control is alpha L is less than 1, and that is what we really see in numerics. So it is very, very possible that the product of alpha L, when L goes to infinity, will converge to something non-zero. Quite possible. And the main proof of this theory is telling people that, well, this cannot happen. The main reason is because we can control the phase difference by the amplitude difference. However, as I mentioned, the convergence may be so slow so that you can never see the convergence in your lifetime. Maybe after 10 billion times 10 to the 10 billion iterations, you get convergence, but nobody wants this kind of algorithm. So we need a better way to deal with it. For general phase retrieval problem, I don't have an answer. I cannot do anything. We have to design new algorithm. But for tychography, we can do something. It turns out to be a very interesting relationship in between this phase retrieval problem and my previous work in vector diffusion maps and this phase synchronization business. Okay, so the second part, very quickly tell you the algorithm about how to combine both algorithms to achieve something useful. So just remind you that this is the mathematical framework. You have an object psi, and you have k elimination friends, and you get this A is fz absolute value, and z is q psi, and so on. Now we can just apply the iterative algorithms, which might converge very slowly, blah, blah, blah. How to resolve this limitation? So, inspired by the people in the optimization field, we consider the following nonlinear optimization problem. We combine both facts in alternating projection algorithms in one functional. We consider this minimization problem. Zeta is actually phase. is a vector, so that every entry is of norm 1, and it contains the phase. What I do first is I multiply zeta by A. That is, I fit the image data, I get something correct, amplitude. Then I multiply in front by I minus PFQ. I want to satisfy the constraint, that is the phase, should be correct. And now I say, let's do the minimization. Ti is not very friendly. We can always do something. Then what can we get? Not very easy. But if you do some calculation, you will see that if zeta is really the ground truth, then this guy is 0. So somehow the minimizer is achieved by the solution. Okay, this is the hint. But it is still not very easy to work with this guy. So we simplify it a bit. You just do an expansion. This is square, so you can expand everything. And A has the fixed norm, so you can remove it, and so on. So in the very end, you get the argmin of zeta star PFQ zeta. And you can imagine that if zeta is solution, maximum is achieved. So we ask our own question: is there any meaning of this functional? If there is, what can we do about it? And the answer is yes. After some tedious calculation, we realize that it is phase synchronization. How does it look like? I will give you the tedious, ugly expansion of this term. The ugly expansion on the left and right-hand side is the result of the calculation. Interpretation is the following. The first summation means that if there are two illumination windows, I and J, and they overlap to each other, then we want to consider the relationship among all the vertices inside these two illumination windows. You can just think in the other way. Suppose you have a function and you have two windows, and these two windows has disconnected support, and you do Fourier transform. You won't expect to have any relationship in the face of their Fourier transform. But if you have two windows, and these two windows have some overlap, that is their support are the overlap of their intersection of their support are not empty, then you might expect that their phase, the Fourier transform of these two areas, will have some relationship. And this is the main idea behind it. Everything we are working on, we are talking about is nothing but Taylor expansion of Fourier transform in this kind of thing. Then, why do I say this phase synchronization? Notice that zeta, when I say zeta, contains the phase information. And this zeta j, qj means the phase of the qj's pixel of the j's diffraction image. And you see that the phase of the jqj and iqi has some relationship associated related to this term in the middle. It turns out that very interestingly, this term is the Fourier-Wigner distribution of some function omega ij, which is related to the how two images are overlapped. So, and we know that Fourier-Wigner distribution is also called ambiguity function, which is related to radar. And we know that radar in radar system, this ambiguity function is used to determine if it is easy or hard to distinguish two objects and so on. So somehow in the very end, we are working with this kind of thing. And there are some terms which we can forget. So this formula tells us what? It tells us that if zeta is the correct answer, is the right phase, then they will be related pixel by pixel associated with this term. So it hints us to build up the following network. The network from all the diffractive images. there are 4 diffractive images here, and there are 9 pixels in each image. If two images are overlapped, then we have all relationship among all the pixels, and so on. We build up a graph, JS image, and for each pixel we denote it as IQI vertex, and with some edges called IQI, JQJ. So what I'm saying up to now is telling you that I build up a network or a graph from the diffractive images. Sounds a bit weird, but it tells us it is oriented by some information derived by FQ operator. But still, even we know that there's a graph, that something looks good, still it is non-convex. So we will try to relax it. How to relax it? Before relaxation, we think a bit more. Recall that the amplitude information is very important. When you want to recover an image from the Fourier domain, the larger the amplitude is, the more important its associated phase is. So we want to do our best to recover the phase so that its associated amplitude is large. And if the amplitude is small, we can just ignore it. So what do? We just define a threshold matrix, which is a diagonal matrix. We say if amplitude is greater than epsilon for some value epsilon, then we preserve it. We put 1. If amplitude is less than epsilon, we just set it to 0. We ignore it. And we consider its TA, PF, QTA operator. Then we evaluate its largest eigenvector. What does it mean? You will see later. But after evaluating the largest eigenvector, V0, we can estimate the image back. It's a spectral method. As you can see, we evaluated only one top eigenvector. So it's quick and scalable to big data. So the algorithm we'll propose is we start from TPS, which we call thresholding phase synchronization, which I showed you. And I run an alternating projection algorithm, and I can reconstruct the image. And this is the result, numerical result. You have Barbara. If you do nothing, you start from random phase. In the very beginning, you cannot see anything. After 100 iterations, you can recover Barbara back. But well, reasonably good. Then this is some objective functions we follow. You can see that it converges, but not slowly. Now we consider this TPS algorithm. We estimate the phase from this spectral method, and this is the result of the estimated phase. Just compare this one and ground truth. It's not that bad. And as far as we know, very close. Then we run 100 times iteration. We get the Barbara back quite well. And this is a convergence thing. Only 4 steps, you get almost everything. I mean, but you may say, okay, well, these 2 images looks quite the same. What is the difference? This is the difference. You see, in this Barbara, if you start from nothing, there are some artifacts. Suppose in a scenario that you only have limited computational resource, I only allow you to calculate 100 iterations, which is quite common in this kind of business. Then you don't start from this guy, you start from nothing. You may have something artificial so that you get a wrong interpretation. Okay, so this is another semi-real simulation. We have this gold ball, whatever, scanned by SEM. Resolution is 10 nanometer or 15 nanometer, whatever. You can see that if you don't start with the TPS, you just start from AP random phase, you have nothing. And if you start from TPS, you get something which is very close to truth. And that is the result you can see. Convergence is quite fast. Okay, so first thing first, we have this TPS algorithm. We want to understand it better. Why does it work? It cannot be just an algorithm. There must be some reason. The reason, as I will discuss now, even though maybe I'm running out of time, is the connection graph Laplacian, which is related to the connection Laplacian in the manifold setup, which I would very quickly describe. And if you have interest, we can discuss later. What we have is we have a vertex, we have a graph, and as I told you, we have this Fourier-Wigner distribution. So from this graph, we can build up the relationship graph. First is the weight, which tells you the relationship among two vertices, which is defined by A. As I told you, we want to take A into account, and the modulation of the ambiguity function, Fourier-Wigner distribution. Then we can define relationship group, which is just the middle term, which describes the phase difference. And there will be something we need to compensate, which is to correct the phase ramping from the length. And the reason is you have to go to the calculation and we will see it. Then you build up the CGL, connection graph Laplacian. C connection graph Laplacian. What you do is, okay, here I simplify the notation a bit. What you have, you build up a big matrix S, and it is in this example, it is Km squared by Km squared complex matrix. You put Wij, Gij in the ij's entry if there is an H and 0 otherwise. And you define the weight D, weight matrix, which is diagonal D, which is summation of all neighbors, all the weights on the neighbors. Then if I give you a vector V, which is R, 2Km squared, so this should be C Km squared. Then you evaluate, this should be 2 by R, this should be 1. I mean, I just mixed up with a general theory. This is D inverse S vector. If you do calculation, you get this formula. And if you are familiar with this regression business, you will see that it is very close to Nadarra-Watson kernel regression, or maybe random this Markov process thing. Yes, it is. When Gij is 1, that is, you don't have any relationship, you get graph Laplacian in the very end, which is just the random work on the graph. Okay, and why is it a random work? Because if you take a look here, now Gij is 1 and V is real, then this guy, if you circle this guy, it just describes you the probability of jumping from point J to point I. And if you have really Gij, then what it tells you is when you jump from J to I, you have to do some modulation. This kind of modulation is encoded in a system. The system tells you that you have to do this kind of perturbation so that you can do something. Okay, well, and the phase is in our case is the phase. And there is a theoretical understanding of CGL from the manifold setup, which tells you that, I will just very quickly tell you, there are some theory tells you that this D inverse S matrix will converge to the connection graph Laplacian on the manifold if you consider a frame bundle and its associated vector tangent bundle. And also it will converge in a spectral sense. That is, the I's vector field, I's eigenvector will converge to the I's eigenvector field of the heat kernel of the associated connection Laplacian. There's several details, but the only information you need to know is it tells you that the top eigenvector of D inverse S is actually the most parallel vector field on the manifold. What does it mean? It means that it will follow all the rules you set up in the graph. And remember that in PFQ, the rule is the Fourier-Wigner distribution and the this phase ramping. What it tells you is what this theory tells you is finding the top eigenvector. The top eigenvector will follow all the rules you set up in PFQ, and in this way, you are able to reconstruct the phase. So what you do is you just evaluate a top eigenvector of D inverse S, the same thing as we discussed before. Spectral method, only top eigenvector can be scaled up. And there are more details about the theory, for example, when there are boundary, non-uniform sampling, or even you can use principal bundle to quantify. For example, if you want to do this nonlinear deformation registration in medical imaging, you can put in this way, or you can evaluate geodesic distance by the eigenvectors of this matrix, and so on. And there will be one more small trick which you can play with, because we know that we really get some heat kernel back. And when we know that it's a heat kernel, so there will be some kind of fluid diffusion scene inside, and this diffusion scene hints us to consider this multi-scale scene. So we can consider long-range diffusion, long-range phase synchronization. The main idea behind it is you have this image for every frame. In every step of iteration, you evaluate an average phase, and you synchronize around all the images, and then you update your PFQ. Okay, and the final algorithm, if you put everything together, we will call synchro RA or synchro AP or synchro whatever. So this is a numerical result, which is from Barbara image. The size is this guy, and there are roughly 10 to the 7 vertices, and the edges is about 10 to the 10. It's actually a small image, and for this guy, if we run 2,000 iterations on my computer, not this one, a small desktop with GPU, it only takes 2 minutes. So it's kind of reasonable scale and can be scaled up because everything is spectral. Now you can see that if you run traditional AP, it needs 2,000 steps. It cannot go to anything reasonable. And in the beginning, it is very frustrating. You don't see anything difference. Okay, but if you start from TPS and the synchro RA, only 50 steps, 40 times faster, or even they try to run it up to 3,000, so it should be 60, but we just demonstrate this. Okay, so another thing is the challenge of the big data in the near future, where I'm running out of my time. So I just show you that the data is growing crazily, and this is nowadays data size. They are giving us difficult time. So, and this is the new era scene we have in Lawrence Berkeley. They have this. In the end of this year, there will be some kind of 10 gigabytes data per second. I still don't know how to handle this. But anyway, I'm a numerical guy, so that is there. Just help them to develop algorithm. And the take-home message is we have global convergence alternating algorithm, which has been open for 40 years. And this phase synchronization, graph connection Laplacian can help you. So this will be a first theoretical guaranteed algorithm in the field, which helps you to get a very big sample in atomic resolution. And sure, it's far from ideal. There are several open problems inside, and we are working on this. Thank you for your attention.
Okay. Thank you very much again for.
Yeah.